Hello everyone. Today is the lecture 2 for communication engineering KC 401. In last lecture we have discussed basically basics of signal system for communication engineering and frequency domain signal like that. Now in this class we will discuss basically energy, power and bandwidth of the signal and related things with these topics. Next, here in the introduction of communication engineering, we will discuss the energy of signal and power of signal. See, there is a signal xt in continuous time domain. We can, it is suppose xt, okay, and it's at one point, suppose it is an voltage or current, at one point its instantaneous power equals to mod of xt square, either voltage square or current square. We can find its instantaneous power. When we integrate it over one period or like that in a duration something, suppose minus t by 2 to plus t by 2 mod of xt whole square dt, it is nothing but the energy of the signal, energy of signal in the duration minus t by 2 to plus t by 2. Okay. And from the same equation we can find its average power of signal, that is its average, then we can find it as 1 upon t integral minus t by 2 to plus t by 2 mod of xt whole square dt. Okay. This is the average power, but average power in this duration minus t by 2 to plus t by 2. Okay. While if we take t tending to infinite, okay, and the when t tending to infinite and energy lies between 0 to infinite, then it becomes a energy signal, and then energy E equals to limit t tending to infinite minus t by 2 to plus t by 2 mod of xt square dt. That is in the complete period, complete duration minus infinite to plus infinite mod of xt square dt. If you are getting energy finite value, then its energy can be calculated using this one. Okay. And average power, okay, similarly the average power when t tending to infinite, then average power of signal equals to limit t tending to infinite 1 upon t integral minus t by 2 to plus t by 2 mod of xt square dt. Okay. And here again, if this power is a finite value in the in that is its power p, it is 0 to lies between 0 to infinite, then that signal known as the power signal, and its power can be calculated using this one. Okay. One more thing which we can add here, that in time domain we can calculate energy and power in this way. Okay. Similarly, in frequency domain, this is the signal xt, its frequency domain signal, its Fourier transform, suppose something like this. this is the x j f. Okay. This is the Fourier transform of this signal, that is the frequency domain signal, okay, can be given by this one. Okay. And if you have calculated x j f, then similarly its instantaneous power also can be calculated using mod of x j f whole square. Okay. And energy of signal can be calculated using Parseval's relationship. Okay. Then it can be given using its integration, energy of signal, sorry, okay, this is mod of x j f whole square d f in the given frequency range, that is minus w by 2 to plus w by 2. Okay. Then we can calculate its energy, okay, of signal in using the frequency domain signal like this one. And this relationship basically you can see using the Parseval's relations, you can equate these things. Okay. And similarly average power of signal, that also can be calculated using in this range 1 upon t and this one minus w by 2 to plus w by 2 mod of x j f whole square d f. Okay. And infinite time duration signal, then this energy becomes limit t tending to infinite, that is not required here, and this is integration minus w by 2 to plus w by 2 mod of x j f square d f. Limit you can say if it is function of t, then limit t tending to infinite, okay, energy can be calculated in this way. And similarly average power of signal also can be calculated in frequency domain, limit t tending to infinite 1 upon t integral minus w by 2 to plus w by 2 mod of x j f square, mod of x j f square d f. This is the method to calculate energy of the signal and average power of the signal in this way, okay, in time domain as well as in the frequency domain. Okay. Next we can discuss about energy spectral density and power spectral density, autocorrelation and cross correlation functions. Then energy spectral density, basically when we are calculating energy E equals to in frequency domain, then in the range minus w by 2 to plus w by 2, okay, this is the bandwidth mod of x j f square d f. Okay. This is the way we can find the energy of the signal. Okay. And one more thing, this also can be written in terms of omega, it is w and omega is different. Then whatever the bandwidth in terms of omega, okay, it becomes mod of x j omega square d omega, and d omega because df, then 1 upon 2 pi appears here, and whatever the frequency range that can be put there. Okay. Then this is also the way to calculate the energy of the signal. Okay. Here if we see that suppose energy per unit hertz, there is a quantity, that is the energy spectral density. Okay, if energy spectral density is a function, that is the GF, suppose, then if energy spectral density is given, then E can be calculated, okay, using energy spectral density GF DF in the given frequency range, whatever. Okay. Now, if we equate this one, then we can say then energy spectral density GF is nothing but the mod of x GF square. Then this is the energy spectral density. Okay. And similarly, we can find the power spectral density. Okay. Then suppose firstly power spectral density equals to S function of f. Okay. If signal is x, then you can say this is Gx, and signal x, then power spectral density Sxf. Okay. Then we can find power P is equal to integral Sxf df in the frequency range, whatever frequency range, okay, given, and P, then using power spectral density, P power can be calculated using this one, and from the last slides, P was nothing but the limit t tending to infinite 1 upon t mod x JF square df. Okay. Then here if we equate this equation for power to this equation, then we can say Sxf power spectral density is nothing but the limit t tending to infinite 1 upon t mod of x JF square. Okay. This is the power spectral density. And if we correlate energy spectral density as well as power spectral density, then energy spectral density is mod of x JF whole square. Then if we put here, then power spectral density is nothing but the limit t tending to infinite 1 upon t, and this is the energy spectral density. Okay. Then this is energy spectral density and power spectral density and so on. Okay. Next, autocorrelation and cross correlation functions. Okay. To discuss that, autocorrelation and cross correlation function, before that, suppose there are two signals x1t and x2t in the time domain. Okay. Then its convolution, linear convolution, suppose that is yt, x1t linear convolution with x2t. Okay. Now, the linear convolution equation can be written like this: x1 tau x2 t minus tau d tau. Tau, it may be minus infinite to plus infinite, that is the complete range. Okay. This is the linear convolution equation. Linear convolution. Okay. Now, autocorrelation and cross correlation, it is represented by Rxt, and if we have to find the linear autocorrelation of x1 signal, okay, then Rx1t is nothing but the integral x1 tau x2 t plus tau d tau, okay, in the complete range, not x2, x1, it is the x1, it is the x1. Okay. Then autocorrelation function autocorrelation function given by this equation, okay, and cross correlation function, that is you can say this represented by r x 1 x 2 function of t. This is given by x 1 tau x 2 t plus tau now d tau. This is the cross correlation function of the signal x 1 t and x 2 t. Okay. Along with in the range minus t by 2 to plus t by 2, limit t tending to infinite and 1 upon t also. Similarly, here minus t by 2 to plus t by 2, 1 upon t and limit t tending to infinite. This is the autocorrelation and this is the cross correlation. Minus t by 2 plus t by 2 यानी means minus infinite to plus infinite, that is the complete range. Okay. And this autocorrelation function related with the basically power spectral density. Power spectral density PSD, that is the SXF, is nothing but the, for x1 signal, this is nothing but the Fourier transform of R x1 t. If you calculate the Fourier transform of this signal, you will get the power spectral density. Okay. That can be given like that is Fourier transform equation, that is minus infinite to plus infinite r x tau or r x t, because we have taken t already, then r x t e to the power exponential minus j 2 pi f t dt. Okay. If we put this value here, then you will get the PSD, that is limit t tending to infinite 1 upon t mod of x1 f whole square. Okay. This is the power spectral density, and similarly cross spectral density, that is S x1 x2 f, that is the Fourier transform of cross correlation. Okay. This is minus infinite to plus infinite r x1 x2 t exponential minus j 2 pi f t dt. Okay. Then cross spectral density can be calculated using the Fourier transform of r x1 t, that is x1 t x2 t, that is the cross correlation function. Okay. Then these are the relationship between autocorrelation and cross correlation. Now come to the next, that is the bandwidth of the signal, Fourier transform of signal and energy of signal in frequency domain. Energy of signal in frequency domain we have discussed already. Okay. Then there is a signal xt, its Fourier transform of given as xjf. Okay. As we have already drawn xt suppose, and its Fourier transform of like this one xjf. Okay. Now here we take normally the bandwidth in this way, okay, but actually it contains the frequency range from minus infinite to plus infinite. Okay. Minus infinite to plus infinite. Okay. And the energy of signal if contains more than 95% in a frequency range, that is minus w by 2 to plus w by 2. Suppose in this frequency range 95% or more than 95% energy of the signal contained, remaining 5% beyond this range. Okay. Then this can be calculated as the bandwidth of the signal. So 0 to w by 2, that will be the bandwidth of the signal. Okay. Okay. its bandwidth of the signal, that is W by 2. Fourier transform already discussed. Energy of signal in frequency domain, okay, that already can be calculated to find the bandwidth of the signal, okay, and then finding the energy, 95% energy in that frequency range, that is the bandwidth of the signal. Okay. This is all about energy, power, bandwidth of the signal. Now, come to the main topic of this subject, that is the modulation. See, basically there is a modulating signal, like that, for example, as we are speaking, then it is an audio signal, we are generating an audio signal and it is continuous in time, okay, and its bandwidth is in a low bandwidth signal basically. Then it is a modulating signal. Modulating signal, our original signal to be transmitted from transmitter to receiver, that is known as the modulating signal. It is a low bandwidth signal, low power signal, okay, and this low bandwidth and low power signal, it has to be transmitted to a distant point at the receiver, okay. For that, if we transmit this signal by increasing its power, then it may be transmitted at the far location with the low frequency, but there are some practical constraints or limitations are obtained, so that we have to increase its frequency, okay. For that, basically there is a carrier signal, that is a high frequency signal, that is a high frequency signal, okay. This high frequency signal is modulated using the amplitude of the modulating signal, and then that signal become a high frequency signal, and with that high frequency signal there are some advantage or some practical things can be obtained, that is here given as a need for modulation. Firstly, the practical length of antenna, okay. Practical length of antenna normally lambda by 2, lambda by 4, and in terms of that lambda by 8, okay. Then antenna length, to make it shorter length, lambda should be very less, then its frequency should be high. If frequency high, then lambda will less, then practical antenna can be implemented. Otherwise, if frequency is low, then antenna length can be high in the kilometers, and that is not possible. So, the modulating signal, low frequency signal, it is mixed with the carrier signal, that is the modulation of the carrier signal, okay. And narrow bandwidth of the modulating signal, basically that is the need, because when frequency is high, okay, when frequency is high, then a low frequency signal is narrow band signal around that carrier frequency, okay. And that is a need, because if it is a wide band, then there are some other noise disturbance can be created. Frequency multiplexing, that is also one need, because if different carrier are using at different frequencies, FC1, FC2, like that, okay, then using frequency multiplexing, multiple signals can be transmitted through the multiplexing. And effective power radiated, because power is directly proportional to L something by lambda square, and lambda square as low as possible, then power will be very low, power will be transmitted through that antenna, okay. Remaining part, amplitude modulation, angle modulation, that we will discuss in the next class, okay. Thanking you.